Good stuff. And a reminder, hopefully, I imagine, we are going to be taking our exam today. So we will be taking it, obviously, like we've done before, at the start of lab and during lab time, obviously, pretty much the same way as we've done everything else up to this point. Um, but before we do that, we will continue lecturing for a little bit, and probably like we've also done before, we'll lay it up a little bit early here today in lecture, give you a chance to kind of get everything together, maybe grab something to munch on or whatever you want to do. And then about 1 o'clock, obviously, we'll meet up there in the exam meeting and take the exam. And then, believe it or not, I think that's it for the week, as Wednesday is a holiday as well. So, that ain't too bad, I suppose. So let us talk about where we've been doing here since it's been a little bit of time. So we're kind of in the Thermodynamics chapter. I think that's 17, if I believe. And a reminder that when we talk about thermodynamics, what we're talking about is really the idea of whether or not a reaction sort of will occur spontaneous oftentimes. So remember that when we talk about sort of a reaction occurring spontaneous, it doesn't necessarily mean that the reaction will occur really, really fast. It doesn't mean that it will occur really slow. It really just means that it will pretty much occur. And that's a lot of what we look at when we look at thermodynamics. As we talked about before, later on, we'll talk about kinetics. And that sort of deals with really how fast or slow a reaction sort of occurs. But here in thermodynamics, we're really focusing on really just that aspect of it, is whether or not under those particular conditions would we expect a reaction to occur. Now, a couple of thermodynamic properties, one of which you were familiar with, hopefully coming in, which was obviously our delta H, which is our enthalpy. And that's usually our heat of a reaction. And again, if it's negative, it's exothermic. If it's positive, it's endothermic. Then in this chapter, we sort of introduced delta S, which is entropy. And entropy is basically, enthalpy is kind of heat. Entropy is kind of disorder. And when we talk about a reaction or something occurring, are we creating more disorder or less disorder? And again, you can look at it as we talked about last time as well, either as, looking at increasing or decreasing disorder, or sometimes people look at it as increasing or decreasing order, which again is kind of the same thing. But basically, if the disorder increases, then the delta S value actually becomes more positive. So the change in entropy actually becomes more of a positive number with increasing disorder. If we sort of decrease the disorder, which is a weird way of saying increasing the order, I suppose, then everything's getting more ordered. The delta S becomes more positive. So that's sort of a different sort of idea that a lot of people have, when we think about negatives and positives, especially when we think about enthalpy. There's kind of three things we talked about with delta S. There's delta S of the universe, which is basically the delta S of the system plus the delta S of the surroundings. And remember, basically, to do the delta S of the system, or a lot of times that's the reaction you're dealing with, you basically take products minus reactants. So you add up all the delta S's for our products, and you subtract it from all the delta S values of your reactants. This is typically a table type value that you would go, obviously, and look up all the formulas. You would want to make sure, as we've talked about as well when we did these, that you find not only what you're looking for in terms of the formula, but you also find it in the correct state. So again, we take products minus reactants. Also, again, if there is a coefficient in the balanced equation, you do take the coefficient into account. So very much like how you do enthalpy, products minus reactants, you multiply the table value by the coefficient as well when you're doing that. So you want to make sure you do that as well. The also a different thing for enthalpy. Let's make that all right. Entropy, that's different than enthalpy, is for things like substances in their natural state. They are, you will find values for them. So that's a little bit different as well. Most of the time, the entropy values are positive values, but you will find things like O2, N2, things like that. You again will find sort of values in that table for it. To calculate the delta S of the surroundings, again, remember that is actually related to the enthalpy, and that's going to be minus delta H of the reaction divided by the temperature in Kelvin. Remember, this negative is important here because, as we talked about in a sort of a normal temperature system or situation, if the reaction is exothermic, it's going to give off the heat and energy to the surroundings. What that's going to do is make the surroundings basically become more energetic and increase the disorder in the surroundings. And the negative delta H and the negative in the formula here gives us a positive S for the surroundings, which again is what we would expect if the disorder would increase in the surroundings. Taking both of those guys together does give us our delta S of the universe, and we can use the delta S of the universe to determine if a reaction is spontaneous or not. Again, if it's positive, then it's going to be spontaneous, this reaction. If it's negative, then it's going to be non-spontaneous. Remember that we can sort of predict as well when you're doing delta S of the system or reaction, sort of the sign that we would expect in that situation based on, for example, if we're dealing with gas molecules. So if we go from a place where we have, say, 2 gas molecules to a place where we have 4 gas molecules, we are increasing the amount of gas molecules flying around. That means there's going to be more disorder, and we would expect it to become more positive, the delta S, and for the reaction, and vice versa. If you started, say, with 4 gas molecules and ended with 2 gas molecules, we're creating a lot more order, and we would expect this to become more negative for our delta S of the reaction in that particular case. Where we sort of finished up, I believe, was we were talking about, excuse me, another thermodynamic property, which is delta G, and delta G is Gibbs free energy. And pretty much like the name implies, it is free energy that's available to do some type of work, basically. And there's a few different ways we'll see to calculate delta G. And as we talked about as well, a lot of times we want to sort of pick the way that, is based on the information that's provided to us. One way that we saw is we could take delta G is equal to delta H minus T delta S. And that's our Gibbs free energy. That's our enthalpy. That's our temperature, obviously, in Kelvin, and that's our entropy. Now, really important in terms of unit-wise here is delta H is typically in kilojoules in terms of the units. Delta S is typically in joules. So you do want to watch out, especially if you're going to use this formula here, those units. Otherwise, you're going to be off by that factor of 1,000. You could convert it either way. Most of the time, delta G is usually in kilojoules, is usually the units associated with delta G. We can use delta G if delta G is negative. It means the reaction is spontaneous. If delta G is positive, it means the reaction is non-spontaneous. And if delta G equals 0, looks like a 6. Imagine that's a G equals 0 is at equilibrium. So we can kind of use delta G to directly figure out if a reaction is spontaneous or not based on sort of the answer that you get there. We also finished, I think, last time with another way that you could calculate delta G, and it's basically the same way as you could calculate delta S and also delta H, and that is basically you could take delta G is equal to delta G of the products minus delta G of the reactants. So same deal as sort of the ones above. You pretty much will go to a table here. That's the delta G of formation. And that's basically your table value that you would look up. And again, you would look up all the values on the product side, add them together. subtract it from all the values on the reactant side, and then you'll get an answer, obviously, at that point. Also taking in the coefficient into account and multiplying by the coefficient. So at this point, there's a couple different ways you can calculate delta G. And as I mentioned earlier, if you're given a problem where they give you a delta H value and delta S value, then probably the top way there is the one to go. If you're given really no information other than maybe the chemical equation or reaction, then probably go to the table and look up the values and do that. The little knot that we sometimes see in a lot of these formulas a lot of times represents sort of standard conditions. And when we talk about standard conditions, so a lot of times you see that little knot on things. Sort of standard conditions is what that means. And basically those are like table conditions. And what that means is typically the temperature is 25 degrees Celsius. If you're dealing with any type of pressure, it's usually 1 atmosphere. If you're dealing with any type of concentration, it's usually 1 molar. So, a lot of times you'll see these little knots, and you can kind of, one way to sort of think about it, is just that it's under sort of these standard conditions. That was a mouthful. Any questions on any of that stuff? I think we talked about last time there. Okay, so let's see where we did leave off here. So obviously I scribbled on this page, so I'm assuming we talked about it. There we go. I scribbled on that page, so I'm assuming we talked about it. So I think where we actually left off was right here with this examples. So why don't you take a few minutes here and calculate the delta G for this reaction. And is it spontaneous at 25 degrees Celsius? The values that you would normally find in a table are up here at the bottom of the screen. So see what you come up with here. This situation, we're looking for the delta G, which is the standard free energy or Gibbs free energy. And really, this is the only piece of information given to us. So in this case, we would want to do our products minus reactants. And again, we would go to the table, find those values. So that means that for our product side, there are 12 CO2s, which each are minus 394.4. Just make that 4 bigger. And then we're going to add it to our other product, which is actually water in this case. And again, we would want to make sure we do look it up for the right value there, and liquid, gas, or solid. And that means we have 6 times our water value, which was minus 237.2 kilojoules. That takes care of all of our products. We're then going to subtract it from our reactants, which would be 2 times our benzene here, which is 124.5 plus 15 times 0. So something like O2 for the values of like delta H and delta G are going to be 0. But remember, delta S, you will have an actual number for something like that. So again, delta G, kind of like delta H in that sense, anything sort of in a standard state will have a value of 0. You'll probably find it on the table and 0. We do all that good stuff there. I believe we end up with minus 6405 kilojoules in terms of our answer. Any questions on that calculation there?
Professor, don't we ignore anything that is not of the gaseous state?
You don't. When you're doing delta G, you take everybody pretty much, liquids, gas, solids, whatever they may be. So there's no ignoring in this delta G calculation.
Okay, thank you.
Yeah. The only thing is, for example, you things like this, for example, in a standard state, you'll find it as zeros on the table. So, sometimes people, just leave that part off of the calculation, but it's more so because this is a delta G value of 0. Other questions? Okay. So is this reaction spontaneous? Remember, for delta G, we can simply look and see that it is negative. So that means our delta G naught is less than 0, which means that it is going to be a spontaneous process here. Any questions on that there? No. So again, in this situation, we wouldn't want to for example, go and calculate the delta H and then go calculate the delta S and then use G equals HT delta S, because obviously we could just directly go and look up these delta G values and calculate it directly kind of that way. So again, sometimes people get confused as to when to use what equation, especially for delta G, since there's a few different ones. And like I said, I've seen people in this situation go to a table, calculate that, go to a table, calculate that, and then calculate that, which you would not want to do, obviously, because you could just go to the table and calculate the delta G. So keep that in mind, kind of solve them based on the information that's sort of given to you, and that's a good approach. Now, also very common in sort of thermodynamics is, as we talked about, they oftentimes in problems may not actually give you numerical values for certain things. They may just tell you, hey, this guy is positive, this guy is negative. Would you expect this reaction to be spontaneous? So for example, if we look at this equation here with our delta H and our delta G and our delta S, remember in terms of units though, this guy is kilojoules, this guy is joules. So this guy's got like 1,000-fold jump usually on this guy to begin with. So keep that in mind as we kind of talk about our different combinations. So for example, if they go, hey, the delta H value and the delta S value, the delta H is positive and the delta S is positive. What does that mean? Well, it means this guy's positive. This guy's going to be positive, which means the reaction will only be spontaneous at high temperatures. So why would it be spontaneous at high temperatures? Well, again, because this guy's kilojoules and this guy is joules, we need a really high temperature here to get the back part of our calculation here to be larger and thus negative overall for our delta G. So at lower temperatures or at low temperatures, this reaction is non-spontaneous, but spontaneous in the reverse direction. If our delta H was positive and our delta S was negative, what would that do if we sort of switched that around? Well, if we then made this guy negative, positive on the first one, negative from the subtracting, and negative from the delta S, temperature is going to be positive. Negative, negative turns it into a positive. So no matter what you do, you're always going to get a delta G that is positive in that situation. And because it's positive in that situation, that means no matter what you do, the reaction is going to be non-spontaneous because of that. Now, if we had a negative delta H and a positive delta S, let's see what that does. So let's scratch this out here. So if this guy was negative and this guy was positive in this case, well, negative delta H and basically positive delta S means that the back part of this calculation is going to be negative, along with the front number is going to be negative. So no matter what you do here, the delta G is always going to be negative, which means it will be spontaneous. And what I mean by what you do here is in terms of temperature, no matter what temperature you got going on there, you're going to be spontaneous at all temperatures. And really your last sort of combination would be kind of a negative and negative for both of them. So again, here, if we had our first guy negative, our second guy negative. Now, the first negative is going to keep it negative. Second negative, along with the subtract, will turn the back part of this into a positive value, which means as long as you are at low temperatures here, delta G will be negative and be spontaneous. Again, if you get a high temperature at this point, that's going to make the back part more positive than the front part, and you'll end up with a positive delta G. So these are ways you could kind of just look at the formula and think about this is positive, this is negative. What do we expect to occur, in terms of our calculation? You could also just throw in random numbers in there and see what you get. But, this is sort of an easy way to sort of think about it. Any questions on sort of that relationships there? So let's talk a little bit about a reaction and sort of the role temperature does play in whether or not a reaction is going to be sort of spontaneous. So let's take a look at this reaction here, a little decomposition of calcium carbonate. We're going to produce some CO2 gas in this case. And it was found that the delta H for this reaction was 177.8 and the delta S was 160.5. So I tell you what, why don't you take a second here and calculate the delta G naught here at 25 degrees Celsius and determine, is it spontaneous, this reaction at 25 degrees? So take a moment or two and see what you come up with. So let's see what you came up with here. So this would be a case, obviously, we were given the delta H, delta S values. So again, probably this formula would be the most appropriate here to use. Again, the one that has the S and the H sort of in there. So if we put that in here for 25 degrees Celsius, remember temperature does need to be Kelvin. So add a 273 to that, gives us 298 Kelvin. That means that our delta G naught would equal our delta H, which is 177.8 kilojoules. I'm going to multiply mine by 1,000. And the reason I'm doing that is to convert it into joules. And I'm doing that because my delta S is in joules as well. Remember, when you use this formula, you need to do some type of conversion there to get them in the same units. Minus our T, which is 298. And because I converted my delta H into joules, I could leave my delta S in joules, and I should be okay. That's going to get me about 129.97. No, that's not. That's going to give me one more here. Hang on. When I do that calculation, it's going to get me here 129,971. These would be joules. Remember, delta G is usually in kilojoules, so we'll divide by 1,000 and kind of move it over, giving us roughly 130 kilojoules for this particular reaction at 25 degrees. First off, any questions on the calculation there? You obviously could convert the delta S into kilojoules and get the same answer. Is this reaction spontaneous at 25 degrees? And the answer is no, it's non-spontaneous at 25 degrees Celsius. Is this what we expected to happen? Well, if we think about what we just talked about, our delta H was positive here. Our delta S was positive here, which means the only way for this reaction to become spontaneous is at high temperatures. So 25 degrees Celsius is not necessarily considered very high, so we would expect what we got there to be correct. Any questions on that so far? Now, we know at 25 degrees Celsius, it's not going to be spontaneous. We also know that in order to get it to become spontaneous, we need kind of a high temperature to do that. Can we figure out at what temperature it becomes spontaneous? And the answer is yes, we can. And we could actually do this by using the same formula there that we used previous. Well, we know it's going to become spontaneous when this guy is negative, and usually to become negative, you need to be less than 0. So we'll go with 0 there for delta G because of that. Gives us delta H minus T delta S. Bringing our minus T delta S to the other side gives us T delta S is equal to delta H, gives us T is equal to delta H divided by delta S. We can put these numbers in. Again, we got unit situation here. You got to do some type of conversion. Again, I'm going to multiply by 1,000 my delta H value to convert it to joules. You could, again, divide the delta S by 1,000 to get it to kilojoules if you like. We're going to do 160.5 joules per Kelvin. And if we do all that good stuff there, we will get a temperature here of about 1108, we'll call it on the round, Kelvin in this case, because this is technically Kelvin, which if we subtract 273 from it, gives us 835 degrees Celsius. So technically speaking, I would say 835 degrees Celsius is, yeah, it's a pretty high temperature there compared to obviously 25 degrees Celsius. So in this particular reaction, we would need to get it to a minimum of 835 degrees Celsius in order to turn this reaction into a spontaneous reaction. Question on that calculation there. So this equation is sort of helpful for a couple of things. It can directly kind of tell you whether or not a reaction is spontaneous. You can also then use it like we did there on the bottom to figure out if a reaction is not spontaneous or not going to be spontaneous at a particular temperature, what temperature you would need for it to become spontaneous. Do we see that represented in the graph that's on this page here, since we have a graph? And we do. We actually start seeing right here at about 835, we actually get up to 1 atmosphere in terms of pressure. That's like, again, standard pressure. And that's, again, when we would consider that reaction spontaneous. Does it start to peak a little bit before that? It does, as you can see here. But it really doesn't reach that sort of 1 ATM level until you get to about 835 degrees Celsius, which again is considered sort of standard pressure and sort of this reaction becoming spontaneous. Any questions on that calculation there? How to do the first calculation or the second calculation? Okay. So why don't you give this one a go here. Following reaction, delta H is minus 1204 and delta S is minus 216. Are the reactants or products favored here under standard conditions? Let's see what you come up with here. Use our equation here. And again, we wouldn't want to do products minus reactants because we have these values given to us, so no need to kind of do those things. Really not much going on here other than we're going to plug it in, except we just need to be careful on units. So again, my preference here, I'm going to multiply by 1,000 to get this guy into joules. That's going to make sure our temperature is also in Kelvin, and that's going to give us a minus 216.4 joules, basically. And Kelvin's here as well. So if we do all that, looks like maybe negative 1140 kilojoules here. Question on that calculation there. And again, obviously you get, I divided it by 1,000 after I got the answer there. So you got a few extra zeros on that in terms of joules. Right back there. So that means our delta G here is negative, which means this reaction is going to be spontaneous. And we would expect, since it's going to be spontaneous, it to head in this direction towards our products in this particular case. Any questions on that particular one? Again, you know, when you actually get the number here, you get 1139512.8 joules, and then divide it by 1,000. Now, does this make sense based on sort of what we were talking about as well and what we were given in terms of our values? Well, again, we were given this as a negative number. We were given this guy as a negative number. Remember, those two negative is going to turn the back end into a positive number. And because this S is in joules and this guy's in kilojoules, the only way it can become non-spontaneous is we would need a really high temperature. And in this case, 25 degrees is a low temperature or normal sort of temperature. And that's why the negative part here overtakes it and why we ended up with a negative value when it was all said and done. Questions on calculating delta G using delta H and delta S. Okay. So let's talk then about what happens as we do something like phase changes or phase transitions and Gibbs free energy. When we transition from, say, solid to liquid or liquid to gas, I'm going to say that right, liquid to gas, that's what I want to spit out. Those transitions are basically in equilibrium with each other, right? So as we go from, say, solid to liquid back to solid, right at that point, they're in equilibrium between the two phases. So if you think about ice and liquid water, you got ice on this side, you got some liquid water over here. But in the middle, you got kind of like ice crystals, if you will, kind of like some solid, some liquid. And again, it's not until you get a little bit above or a little below that, you do get either liquid or solid. And as we talked about, I think the other day as well, a reminder, delta H of fusion, right, is what we use there, to the energy required to sort of do that transition, not change the temperature, right? Just simply take it, if this was water, it would be 0 degrees Celsius where that would occur. Same thing happens as we go from liquid to gas or gas back to liquid. We're pretty much at equilibrium at that point. And again, it's not until you get, a little bit above, say, 100 degrees Celsius for water that you get steam, a little below 100 degrees Celsius that you get liquid water. And again, for water, for example, this happens at 100 degrees Celsius. But in between there, you got kind of both things happening in equilibrium with each other. That's why if you ever remember kind of a heating cooling curve, there's these kind of flat points along the way. If that's like steam, for example, that's like liquid water. And that's like ice. This would be something like 0 degrees Celsius for water. This would be something, let's borrow that 100 degrees Celsius there for water where those transitions occur. Now, because we would be at equilibrium in a process such as this, so here's liquid going to gas. This is basically evaporation, right? Or vaporization happening here. And because we would be right at that point, we would be a delta G would equal 0. And by doing that, we can rearrange that delta G equation to solve for the delta S. And when we do so and we rearrange it here, we get this expression here, which is the delta H divided by T in Kelvin. What are these values? Well, a couple of things here. First off, the delta H here for this case would be the delta H of vaporization. So that's the delta H of vaporization for water. It's about 40.8, 40.7 kilojoules, or about 2,260 joules per gram. So that is the delta H of vaporization for water. When does this occur for water? As I just mentioned above, it occurs at 100 degrees Celsius, which means if I add 273 to it, gives me 373 Kelvin. That is where the number here comes from. That is the normal boiling point, right, for water, which is 100 degrees Celsius or 373 Kelvin. So if we put these guys together and we're assuming that we are going in sort of this direction here, going from liquid to gas, that would be an endothermic process, and this would be 40.79, and we end up with 109 joules here in terms of our entropy of vaporization is what this is sometimes referred to, the entropy of vaporization. What does this number mean, this 109 number? Well, this 109 number is a positive number. And does that make sense? Well, an entropy value that's positive means that the amount of disorder is increasing. And that is what we would expect in this situation, because we're going from liquid, where everybody is sort of together pretty close to each other, to a gas phase, right, in a sense, where we got everybody has broken apart from each other and is flying around. And that would result in more disorder, and we would expect this value here to be a positive number. Question on that? Could also do something like the delta S of fusion if you were doing this transition here, solid to liquid or liquid back to solid as well. Now, what would happen if we specifically wanted to know, we started with water in the gas phase and we were heading to water in the liquid phase? What's going to happen in this situation? What would be different with the calculation here? Well, delta S would equal delta H over T. Only difference here is if we go from gas to liquid, we are doing a exothermic process, which means this value technically would be a negative value. Temperature would still be the same, happens at 100 degrees Celsius. And the only difference is we would end up like minus 109 joules. The minus here is significant because as we go from gas back to liquid, we have things flying around crazily, and then it's going to become liquid and things are more ordered. And we would expect a delta S here to end up as a negative number, which it does, as we are going to become more ordered here, or an ordered type state, as opposed to over here where we're becoming more disorder, right? Question on that calculation or idea there. What is the other really important thing about sort of manipulating this equation and solving for something like the entropy of vaporization or fusion? It is the actual equation itself. You might look at this equation and it might look very familiar to you. We have this delta S is equal to delta H divided by T. That is, for like vaporization, which we just talked about, not to be confused with the delta S of the surroundings, which is minus delta H divided by T. So very common, these two guys get confused a lot. The main difference is really this one here. It's sort of the surroundings has that negative. This guy does not have the negative built into the formula, as opposed to the delta S of the surroundings does. So that's a really important thing to sort of keep in mind when you should have that negative or you should not have that negative in there. And again, the negative should be in the formula when you're talking about the surroundings. If you're doing some type of phase change, it is really based off of this equation here, and there will be no negative involved. So that's an important thing that sometimes people get a little bit confused on. Other important thing is obviously if we're not dealing with water, boiling points, freezing points will be different temperatures, and also heats of vaporization, delta H is of vaporization, delta H is of fusion, will also be different values if the substance is not water. So, if they give you some other type of substance and they don't actually give you either the normal boiling point or freezing point or melting point, and they don't give you the delta H of vaporization for that particular guy, you want to make sure you find it for the actual substance you're looking for and not just automatically always use water values. Any questions on that? All right, why don't you try one here, see what you come up with. We'll talk about it. Base is 58.5, and the normal boiling point is 630. What is the entropy of vaporization? So we're assuming that we are going from, mercury sort of in the liquid to mercury here in the gas phase. And we give us the delta H of vaporization for it as 58.5 kilojoules and the normal boiling point temperature of 630 Kelvin. So as I was just mentioning, these values are obviously different than water. And again, we wouldn't want to use water here as we're talking about mercury specifically. So you want to keep that in mind. Again, we're going to do basically this phase change, which is basically an equilibrium type of process to occur. We're going to assume we're going in this direction from liquid to gas, although that does look like an S. So let me fix that. So again, really based off of our delta G here equation, since it's at equilibrium, this is going to equal 0, which gives us 0 is equal to delta H minus T delta S. Bring in the T delta S part to the other side and dividing by the temperature in this case, since we're looking for the entropy, would give us our delta H divided by T. Again, no negative here. That is for surroundings. So putting it into here, our delta H is going to be positive, assuming we are going in that direction there, divided by our temperature, which is already in Kelvin. And if we do that, we do end up with 58.5 divided by 630. We end up with 0.0929 kilojoules, and which is about 92.9 joules, which again is typically what delta S is given in terms of units. Since our delta S here is in joules, our delta S is positive, again, assuming that we are heading in this direction. If it specifically talked about it going from gas back to liquid specifically, again, the only thing that would be different in this calculation would be that delta H value would be negative, and that obviously would then yield you a negative 92.9 joules when it's all said and done. But in this case, we could probably safely assume we're going in this direction here, and it would end up with a positive delta S, which is what we would again expect to happen as we are going into the gas phase and creating a lot more disorder. Any questions on that there? Okay, so I think it's a good place to stop. We'll lay it up here for the